Good afternoon, everybody, or good morning, depending on where you are. We will get started in just a few minutes as people filter in here, so stand by. Okay, I think we are good to go here. We'll go ahead and get started. So again, welcome everybody to this edition of Ask the Moldflow Experts. This is a semi-monthly webinar that we're doing. We're doing one about every couple of months this year. So we hope you're enjoying these types of webinars and various topics regarding Moldflow. This month's topic is windage analysis for tight tolerances, and it's going to highlight a project we worked on for the COVID story. I'm sure you're all sick of hearing about COVID now, but this is a really nice story. It's a rapid Moldflow response that we worked on for a ventilator project, the GM project, if you're familiar with it, also known as Project V. So we'll dig right into that. So just a quick intro to CAE Services. If you've not dealt with us before or know what we're all about, we were established back in 1988. We have the most expert certified Moldflow engineers in the world. It's really not even close. We've got about 15 expert certified Moldflow engineers right now. We are an Autodesk make partner. Autodesk has trusted us that we are experts in our field with Moldflow, so we are responsible for Moldflow software sales, training, consulting, you name it, anything Moldflow, we are doing it. So we've become an Autodesk partner, and it's been a great relationship. We've completed something on the order of 26,000 plus projects since 1988. So we've got a wealth of experience in the Moldflow world. There's our website if you want to learn more about us. Feel free to do so. This is me. This just says basically I've got a lot of background in Moldflow. I've been around for 27 of those years, going back to 1988, 1993 for me, but 27 of the years here at CAE Services. I'm primarily responsible for training and leading the consulting team here. I've contributed to trade magazines and done lots of presentations at the Moldflow Summit, et cetera, et cetera. So, but this was my lockdown experience last year. So I have 4 teenage daughters, and it's starting to show in the gray hair in my head. But so spending that precious lockdown time with 4 teenage daughters was very noisy. And then there's Willie, my little cockapoo. He's also noisy, especially with more people around. My wife was working. She's not noisy, but you know, you can imagine how things were in the Lankish house during this time period. Oops. I also decided that I should get back into shape, so I started running. And it turns out that 50-year-olds really shouldn't take that on full stride from the get-go. So 3 strained calf muscles later, I decided to give that up. So Oh well. And then 2 large jigsaw puzzles. I'm sure some of you probably experienced the same thing. And then we did multiple house projects. So that was my lockdown experience. And going back to a year ago now, um, just a reminder, and we've all heard chapter and verse on this, but the COVID problem was a rapidly changing conditions in March. With the spread of coronavirus. Um, at the time, there was really not much known about how potent it was. I heard all kinds of things, 15 days to flatten the curve, and here we are 365 days later, still flattening the curve. And at the time, everybody thought the best way to treat COVID was, for the very severe cases, was to put them on ventilators. And so evaluating the supply of ventilators, especially in those hotspot areas like New York and New Jersey and so forth, realized that there was potentially a ventilator shortage. It never ended up materializing, but imagine in the panic stages what everybody was thinking, and there was a rush uh, to produce more and more ventilators so that in case this snowballed into something that was uh, extremely severe for ventilators, then there would be a supply available. So that's what we were dealing with a year ago. And so we brought the power of American manufacturing to bear, and it's not just American, but we actually dealt with some Canadian firms too here too. But um, I just want to point out that we've gone through so much animosity over the years politically, the last year I should say, politically and so forth. But when the people in their government have a common purpose, really good things can happen, and that's what happened in this case. And it's amazing to see how many of these stories came out. Seen them in the trade magazines, see them on the news, and so forth. But the plastics industry in particular really stepped up. And it points out in particular, I mentioned our Autodesk relationship. Their motto is "Make anything." Autodesk has a big role in manufacturing, from the design end through simulation and on to the manufacturing side and CAM products and so forth. So it really highlights, that capability. And then, of course, really, in this case, Moldflow's role in the plastics manufacturing sector really stood out. The ability to simulate on the fly and get things done quickly, so that we could produce, all these new molds that created the plastic parts for this ventilator was really something to behold. So just wanted to highlight that. And here's the product that we're going to be talking about. This is called Voxen. Ventilation, oxygen, cough, suction, and nebulizer is what that stands for. Ventec Life Systems is in Bothell, Washington, which is interestingly right near the epicenter of the first cases that came into the United States. This is really the Cadillac of ventilators. I mentioned all those different, what that acronym stands for. It's about the size of a small suitcase, weighs about 18 pounds. That's 5 devices in one, all the things I just mentioned. And Ventec was used to producing about 200 of these a month, which was going to be nowhere near what was going to be needed potentially to help out with the COVID situation. So they hooked up essentially with General Motors, and obviously the automotive industry, for all intents and purposes, shut down during that month of March and April last year, and consequently were available to bring to bear the full power of their supply chain. There was no way that Ventec, with its current supply chain, was going to be able to produce the amount of ventilators that they were going to need. So it was called Project V, and again, it brought GM's manufacturing might. If you want to see the full story, you can go to Ventec's website and check that out. But essentially, the government contracted with GM $489 million to produce lots and lots of ventilators. The Defense Production Act was invoked. The FDA relaxed some of the enforcements on the ventilators, and Ventec was contracted to supply 15,000 ventilators by the end of June and another 15,000 ventilators by the end of August, both of which came to fruition, no problem. And again, in retrospect, these ventilators really ended up not being needed, but imagine if they had been. Luckily we were at the point where enough ventilators would have been produced had it ended up being a problem. This was done in the Kokomo, Indiana plant, as you see on the right here. And GM deployed about 1,000 workers to scale up the production. So they were able to do about 10,000 per month, and they had a plan in place to make it scalable had things gotten worse. So how did we get involved? So CA Services has a long-standing relationship with General Motors. We have our expert certified consultants that work on their projects. GM requires expert certified engineers to work on all of their products. I sit on the GM advisory board, so about once a year, GM has a sit down with all their advisors and talks about Moldflow and what can we do better and what are the best standards. We've worked on probably thousands of GM parts over the years. I keep meaning to count, but I haven't gotten around to that. But in any case, we've done a lot of work for GM. And they know us for our expertise in windage. So, they called us because of that when they got engaged in this project. And we worked on several of the nearly 800 parts that are in this Voxen device. So the one we're going to talk about today is the bracket for the oxygen metering valve. And these are some of the other parts that we worked on as well. This is the oxygen metering valve, a small part that sits in the guts of the assembly here. And you can see the part here that holds the oxygen metering valve. So this was originally machined in Peak a long time ago, and then they changed to a single cavity injection mold. Remember, they're only producing about 200 of these a month prior to the ramp up. So they had a single cavity injection mold. The material is Victrex 450 FC30. It has 10% high strength carbon fiber, 10% graphite powder, and 10% Teflon in it. Some of the existing issues, and this is where the main topic of today's discussion is going to occur. The perpendicularity of this boss needed to be within 2.5 thousandths. Perpendicularity of the L shape within 10 thousandths. As a side note, they had some excessive sink, and this is more due to the fact that this was originally a machined design, so it wasn't the best design for plastics. It's go to plastics 101. There were some things in the design that just weren't done properly. But we are in a rush situation here, and we had to see what we could do to get rid of some of this sink as well. And I really want to hit on this timeline. Whether you're new to Moldflow or new to Windage, one of the big objections to doing analysis or doing windage analysis for that matter is, how quickly can we do things? So this timeline is pretty impressive. Now, again, everybody was kind of shut down, so we were able to pull all of our forces into it. But this is what can be done when things really need to happen and happen fast. So end of January last year, the first case of COVID hits Washington. In the middle of March, the U.S. government engaged GM on the 19th. On March 30th, GM got together with PTI, Engineered Plastics. They were the mold builder and the molder. And then 2 days later, we were engaged. So everything in blue here is going to be our engagement timeline. So April 1st, rather, We had the first Moldflow results based on the existing tool design. We did some material testing on this, and again, material testing can often take 3, 4, sometimes longer, 3 or 4 weeks, sometimes longer. But we were able to have this get done within a week. In fact, 4 days, the material testing was completed. We took that new material testing data and input it into the Moldflow model, and we had new simulation. We had the windage shape. We expanded and morphed the nominal CAD all on that same day. Did our windage check, and then we delivered the final windage model the next day. So, 7 days of work on our end, and we had a fully functional windage model, and that included material testing. So, if you look, really at the time we were involved, it was 1, 2, 3, 4, 5 days, essentially. Or actually 4 days that we actually worked on the project. By the 16th, the windage model was incorporated into the tool, and the tool was complete. And on that same day, the first parts were molded. So pretty impressive timeline, really from the time they engaged the mold maker to the time we had first parts, really 2.5 weeks. So here's a look at the existing mold design. We had a gate on this edge of the part. That's the filling pattern and the resulting fiber orientation pattern. So you notice a little bit of non-uniformity. Fibers going this way, going this way. That was partly responsible for some of the warpage. As I mentioned, we had material testing done in the middle of that, and I'll explain that in a minute. But from the old material deck to the new material deck, didn't see much of a pressure difference, a slight increase in the new material deck. But one of the reasons we decided to get new material testing done is because the old material deck was not properly predicting the warpage. It was predicting the right trend. You see the collapse of that L shape, kind of exaggerated by a factor of 3 there. But the numbers just weren't right. And consequently, with the new material deck, we were able to get those numbers right. You see there's less warpage being predicted. So, if you get these numbers wrong and you try to take corrective action to fix it, then you might cause a whole set of other problems. So we wanted to make sure we had that right. We knew we had very tight tolerances that we were dealing with here. So that's the reason we had material testing done. And this is kind of an overlay. There were some rough scans of parts that were available from the old material deck, and you see the max deviation on that was 14 thousandths, but this front lip here was off by 9 or 10 thousandths, whereas the new material deck, you see things were much tighter than a couple of thousandths. So we trusted the new material deck a little better. Down here, you see some areas. We actually found out later that they had made some modifications to wall stock there, and that the amount that was off was almost exactly the amount of wall stock they adjusted by. So one of the things I love about Moldflow so much is the ability to not only predict the amount of warpage, but to point you in the right direction as to what the primary cause of the warpage is. Now, in this case, it wasn't any surprise that we found out that it was the fiber orientation and the shrinkage variations that are set up by that fiber orientation. That was the main cause of the problem. But sometimes, we see, even with fiber fill materials, we're surprised. Sometimes it's a packing issue. Those numbers are very small over here. And sometimes it's a cooling issue, and numbers are even smaller over here. So we knew it was all about fiber orientation, and we were going to do what we could to try to fix that with more conventional means first. And so we moved the gate, came up with a new gate location. Rather than gating on the front edge here, we gated on the side edge. See what we could do to get all the fibers going in the same direction, to the extent that we could. So you see the fiber orientation is a little more uniform across that top deck. It's not always going to be perfect when you have a single gate on a square like that, but we were able to get fibers more generally aligned across the part. Also shortening that runner system and putting the gate on the side. We also increased the gate size. And we're able to bring the pressure down from 15,000 down to 9,500. So it gives us a little bit more of a processing window to work with, which is always a good thing. So the L-shaped warpage improved. So, the downward deflection was 9.8 thousandths here in the original, and inward it was just under 11 thousandths. And then with the new gate design, we were able to bring that down to 7 thousandths, 9 thousandths. Not a huge improvement. I mean, quite honestly, great, you did some good things, but we're still not anywhere near within tolerance. So now what? Furthermore, we had this boss deflection tilting forward in the Y direction here, some 5 thousandths. We were able to get that down to about 2.8, but remember, we were looking for 2.5. So we knew there was still some work to do there. One of the nice things that came out of that new gate location, here's the original volumetric shrinkage, which is a good indicator for sink. Matched up really nicely with that sink pattern that we saw on the original parts. And then when we switched gate locations, we're on the same scale here. We had a significant shrinkage reduction there. Moldflow also has a sink mark estimate. It's a little bit choppy here, but you see these numbers also came down pretty substantially. So a good indicator that we were likely to see less sink, which was one of the objectives of this project as well. So, we reduced warpage, but there was really nothing else to do from a processing standpoint or gating standpoint to improve on things. We couldn't change the part design either substantially the way we would have wanted in order to fix this problem. So the next step was to go to a Kentucky Windage solution, because as I just said, conventional improvements only get you so far. For those not familiar with Windage, Windage is essentially biasing the steel of the mold in the opposite direction of the expected warpage. So if this center plane here is your intended shape, the target, you may need to bend the steel all the way out to a factor of 1, meaning, if you predict, say, 1 millimeter warp, maybe you have to warp it backwards, bias it backwards 1 millimeter. That's often not the case, though. Sometimes it's half of that, sometimes it's 3/4 of that. It really just depends on the material, the structural design of the part, etc. So that's where the simulation comes into play. So the windage factor is something that needs to be determined. Why is this a good thing to do in simulation world? Because traditionally it's been done by trial and error. You mold some parts, you measure them, see how much you're off, cut a little windage in, see if that takes care of it, mold them again, still off, and you go through that loop several times. So those are called tuning loops. That's expensive and time consuming. And so we use simulation. We're doing this more and more. Now really CAE's been doing this for 10 plus years in simulation world, but the big thing was always who's gonna cut the steel, who's gonna create a CAD file that is moldable, works in the mold design. So we've developed that skill on our own over the last several years, and we've gotten quite good at it. So using simulation to do windage is a really good way to go, because it's less time consuming and less costly. And here's a typical breakdown. This is more for maybe a little bit larger part, but that I've heard of mold builders budgeting upwards of 100,000, 110,000 in this case. This was for a heavily ribbed oil pan. But budgeting this amount of money and this amount of tuning loops and this amount of time to do the windage on these types of parts, and to do it through Moldflow analysis, you get the time that's required to do the analysis work. It's often about a week for us to complete the windage and CAD morphing, windage analysis and CAD morphing. And I would argue even in some cases we're doing that CAD morphing even quicker. And then, I don't want to say this is all 100% perfect. There's often cases where you might have a tuning loop after you're done. But you can't argue with the fact that it's going to reduce the number of tuning loops, and it's going to reduce the amount of time to get there, and it's going to reduce the amount of cost to get there as well. All these, you should also note that a lot of these activities are happening concurrently, so we don't want to be the bottleneck in the process. So we got to determine the windage factor, and you can see here we have to in Moldflow world we have to reverse the Moldflow warpage results. There's no CAD morphing yet, and so we have to test that out. We have to find out what that windage factor is. Do we reverse it by a factor of 1? Do we reverse it by a factor of 75%? Where do we go with that? In this case, you can see what we've got. The purple is the nominal or the target, and the green is the windage file. So you can see it was, excuse me, biased upward so that it could come back down. That's its tendency, if you recall, looking at the warpage animation. Its tendency is to warp down. Also notice the green part is a little bit bigger than the purple one, so there's shrinkage that is factored into the equation here too. In this case, there's no diadrawl corrections yet. So we're just determining the windage factor, and then we got we also have to consider the fact that Moldflow has variable windage. You saw that shrinkage plot for the sink marks earlier. That shows you that shrinkage occurs at different levels within the part. It's an infinite number of different levels of shrink, but mold makers only cut steel to one number. So initially, when we're figuring out the windage factor, it's taking into account this variable shrinkage. We have to run with the same process that we ran when we figured out the original warpage shape. And then we do the windage check. That's the windage check model. So once we determine the right windage factor, and a lot of times it's going to come right in at 1.0, but not all the time. But we overlay that with the original, the target model, and we see that we're got very, very tight agreement with the target shape here. So we know we're right on with a 1.0 factor, and now we have to go the next step. Okay, the next step is CAD morphing, but remember I said that there's an infinite number of shrinkages in any given part, and the molder, or the mold maker rather, is going to cut to one number. So what do we use? Okay, so we go to the Victrex data sheet, and we see in the direction of flow 3 thousandths per inch, and cross flow we've got 7 thousandths. Okay, well, I did my Moldflow analysis, and there's we have the ability in Moldflow to kind of give a composite estimated shrinkage in all three directions, X, Y, and Z. And so it's showing 6.5, anywhere from 6.5 up to 9.3 thousandths there. So, there's 2 data points. We also contacted Victrex and got their input, because obviously they know their material very well, and they were very helpful in the process. They ran it through Moldex, and Moldex was predicting somewhere in the neighborhood of, I think it was 13 to 17 thousandths, which sounded really high. So that's kind of where we were at, and after some discussion and with a good material characterization, we decided on these numbers. So remember the gates over here, and this was the fiber orientation results, and you can see we've got the highest shrinkage cross fiber, and we have these other 2 shrinkages which were kind of in the direction of the fiber. So we ended up on 8 thousandths in one direction and 6 thousandths in the other 2 directions. So that's the starting point, is to expand it by that factor. And then we have to morph the part. So the morphed part is in blue, and the purple part is in the nominal part there. Okay, and the big part of doing morphing for windage is keeping features in die draw, right? So it has to be toolable. You can't be having any die lock conditions, especially on these vertical features here. So we did a windage check on this, and everything seemed to check out pretty well. We did have a couple of dimensions out on the side. This was on an action here, and these were not critical dimensions. So we because they were on action and it was going to take a little more effort, it would have made the tooling more complex on that action. We decided to leave that alone, and so that's consequently why we got those 2 dimensions as probably the largest deviations we saw anywhere in the part. Keep your eye on the top of this boss here too. So first molded samples, as I mentioned, came rather quickly. And the perpendicularity of that L shape, we wanted it within 10,000ths. And they, used a CMM machine, lined it up to the GD&T, and measured 3 parts, and these were the numbers that we got. Okay, so you can see for the L shape, we were still out, or actually those were good, but for the perpendicularity of the boss, we were right on the razor's edge of making that work. So the perpendicularity of the L shape, we're in good shape. Okay, and the cause of that one being out still was most likely because we had to keep those vertical features in die draw for the tooling. So we had to come up with something else. First order of business though is to double check the Moldflow. And if we put an anchor plane at the base here to measure everything relative to that plane, you see Moldflow pretty well nailed it. We had 2.7 thousandths of deflection, where they measured it as well. So that gave us confidence in moving forward with some part design changes there. We also, got some molded samples and noticed that the sink marks were improved significantly by changing that gate location. So that was also good news. So we started with playing around with part designs, and you can see, and I'll just go through a litany of these, kind of put a little moat in here. Max deflection didn't decrease much. We put some ribbing in that moat. Nice, we got down to 1.3. Still playing around with that. This just a different design. We kind of ramped up that moat on one side, down to 1.8. A different moat design again, 1.5. And then my designer came up with this idea of kind of chiseling out some material on that thick wall of the boss. A spring had to fit around this, so we couldn't get rid of that OD. So we just chiseled some material out of there and got the best deflection results yet. Only problem was on this particular chisel out area right here, there was a kind of a keyhole on the backside that was going to cause a very thin wall condition there and cause some backfilling and potentially a non-fill. So we shortened up that one particular chisel out area there and came up with our final design here. And you can see our max deflection in that case was less than 1,000th in the Moldflow world. So we got some final molded samples, and these are the results that came out of a scan. Thank you to Windsor Mold Group for doing some scan work on this for us. And you can see some very tight numbers here. This was just kind of a best fit overlay from the CMM folks, laying it out relative to the G&T nicely. That L shape, those numbers got even better. Perpendicularity of the boss, it's right around 1,000th. Okay, so everything looks really good at this point. And the skeptic here says, well, geez, you're at 1,000th, but your Moldflow predicted less than 1,000. Why isn't it that accurate? And I guess my response is this is simulation. There's uncertainty in any number of variables that are involved in the injection molding process, not the least of which are, material lot-to-lot variability, just any number of things on the injection molding machine, et cetera, et cetera. So, but by making a number of changes, not only to the tool design, but also, employing windage, we are able to meet those tight tolerances. So what did we learn? A couple things. Rapid Moldflow and windage is possible. So, I mentioned at the beginning that so many people are hesitant to use Moldflow, and particularly Windage, because they think it takes a super long time. And it can. I mean, if there's a lot of backlog and so forth at a company, and they've only got one Moldflow guy there, certainly can. And that's why at CAE here we've really taken the time. I mentioned the 15 expert certified engineers. You got to have folks that know what they're doing, are able to do it fast, and are able to respond on large number of parts at any given time. So that's the right people. Experience really matters. The right relationships. We started with Ventec. Ventec got in contact with GM. GM had the relationship with both PTI and with us, and that really mattered. We've worked within the GM ecosystem for a long time, and we know how they work. They know how we work. So it was really kind of a match made in heaven there. Got to have the right software, of course. Moldflow is the standard when it comes to plastics injection molding simulation. And I would argue not just the right software, but I mentioned the right people and knowing how to run it. But you got to have good material data. Very essential. You got to have the right model. You got to be able to make sure you're simulating things as they're really happening in real world. So just wanted to add that. You got to have a common purpose. Obviously this was rush, and it was all hands on deck to make sure that this could happen fast. I've never seen information flow as easily and quickly as it did on this project. And it's mostly because everybody was able to concentrate on one thing, but it can happen. Windage analysis is here to stay. I mentioned previously that we've done a lot of windage analysis over the years, and the question always became, who does the CAD morphing? And it was always stuck on the mold makers who didn't really want to touch it for the most part. So we've developed that capability in-house, and we've gotten very good at it. And we're able to use that along with our windage analysis to provide really a turnkey package for a windage product. And then lastly, we learned that American manufacturing is something to be proud of. So plastics industry all over, whatever you've done to help the COVID situation, give yourself a big pat on the back because it really is something to be proud of. With so much manufacturing being done overseas these days, started to see some of this come back to the USA, and it really shows, what American can do when we put our minds to it. So just wanted to mention that. As far as what's new here, I mentioned the partnership with Autodesk. So software training and mentoring is what we provide on the Moldflow side. I want to really highlight that mentoring side because all the guys I've trained over the years, it doesn't happen just by taking a class. We provide those classes, but it's really the hand-holding that goes on beyond the class. Learning, putting an extra set of eyes on things when you're doing Moldflow analysis to make sure it's being done right, and to check your either biases or whatever it is when you're doing analysis. You got to know when to call BS on things sometimes when Moldflow's showing something that just doesn't make sense, because it certainly happens. So it's all that experience in Moldflow that really helps people get to the other side when it comes to learning Moldflow. So we have the training classroom and online, more online these days, of course. We have these webinars. We also have office hours, which is kind of along the lines of the mentoring. You can sign up for time and with me or whoever to just fire away any questions you have about Moldflow to help you along with your learning experience. And then, of course, our website. You can also follow us on LinkedIn. And now the Q&A. So I had a couple of questions that were posted on the registration, so I'll address a couple of those first. So one of the common themes in those questions was, what are the risks with windage analysis? And I guess the best way to answer is, what are the risks of not doing it? You know, if you're already on board with trusting Moldflow enough to predict things to the point where it's helpful in it's helping you make decisions about how to design your mold or design your part or process your mold, then why not do the windage analysis? So I showed the timeline, the cost. You know, that's becoming less and less of an issue. So really, it boils down to the accuracy. So if you trust the accuracy of Moldflow enough, and you know, and just in a standard analysis, then it's really no different than a standard analysis. It's just using a methodology to get you to a shape in your mold that brings your part back to flat as possible. And all of those things that go into an accurate Moldflow analysis apply. You know, I mentioned having the right expertise, having very good material characterization, knowing which types of models to use at what point. You know, we have 3D models, we have fusion models, we have mid-plane models, all of those things and all of that knowledge, you got to know when to use it and how to use it. So you know, the risks are no different than any other standard Moldflow analysis, really. I would also throw one kind of a side note on that, buckling. I've been burned on this. Parts can buckle if you don't know how to analyze for buckling. You know, this will happen on very large, thin parts, for example. So if you get into a buckling situation, you have a very unstable situation, and windage analysis probably isn't where you want to start. You want to start by fixing your part design first before you get into windage there. Another question, a couple of questions I had from people. How do I convince my management to use windage? Well, again, the proof is in the pudding. You know, this is one example. I have many examples of us using windage effectively. So, you know, try one out, I guess, is the best way to do that. You know, the time and cost issue I've explained at length. It really shouldn't be an issue. So there's no other way than to, you know, have them talk to us, and we can show examples of success stories, and that's, in my opinion, the best way to do it. Another question is this useful for Moldflow Advisor? So for those of you who are not aware, there are two basic levels of Moldflow software. There's Moldflow Advisor and there's Moldflow Insight. They each have their own target audience, really. Moldflow Advisor is more kind of an upfront analysis tool, maybe for part designers, or if you're in the quoting stage of a project, to help you make some basic decisions on whether or not this part is going to be manufacturable. I would not advise using Advisor for windage analysis. The Moldflow accuracy, or the warpage accuracy rather, for Moldflow Advisor is not there to get the kind of accuracy you need to be doing windage analysis. It's more of a trend analysis, so I'll just leave it at that. How or when do I know windage should be used on a given part? So, I mean, you can't always predict ahead of time, but I can tell you certain trends. You know, obviously the tight tolerances, there's only so much you can do in mold design, part design, and processing before you have to throw your hands up and say, this is as much warpage as I can squeeze out of this. So, you know, there's only so much you can do. So some of those cases are, you know, like glass fiber filled materials. You know, it's almost always the case that there's going to be some warpage left over. So those are the cases where you really should start thinking about it. You know, if you think you're going to get into a situation where you're just not going to be able to reach the warpage you expect or the tolerance you expect, then, you know, I would say I would always be considering it. You know, once you see some success with it, it should always be something at the back of your mind. Okay, so other questions that are coming through online right now. What software does Moldflow use to change the mesh windage file to a solid CAD model? So Moldflow doesn't actually do any of that work. This is a technology or a technique rather that we've developed on our own. So we use the mesh, the warp to mesh from Moldflow and do the morphing ourselves separately. Does the grain of a part and depth of the grain play a large role in windage? It can. I mean, there are certainly cases where, you know, if you've got a draft angle, for example, that needs to change because of the morph shape of the part, and you've planned for a certain amount of draft along with the type of grain that you have, then that could certainly play a role in it, no doubt about it. Let's see what else we've got here. What material testing was performed during the characterization of the material that attributed to the increase in warpage accuracy? Well, first of all, I don't remember all the specifics, but I think one of the material properties that I don't think was originally characterized for was juncture loss data. Juncture loss data helps you determine pressure losses in a runner system when there are changes to the diameter of the flow cross section. It's literally just to jump over that barrier from one size to the next. And so consequently, if you have the pressure predicted on the low side and you're imposing a certain amount of pack pressure, it's going to change the shrinkage characteristics of what's going on in the part, and consequently the warpage characteristics. So I think that was one thing. I also think that the material file we had was somewhat old. So I don't know if there was any kind of change to the formulation of the specific material or not, but that was another thing. So in this case, we didn't use midplane. This was much more suited for a full 3D analysis. And I don't want to get too deep into the woods on that, but oftentimes we will create different types of models for the same part. You know, we like to see agreement among all of our different model types when we can. But that's a topic for another discussion. Okay, I think that about covers it. You just check real quick. And one more question about the material properties. It says, is this typical that the material properties are generally not readily available in Moldflow? It's hit or miss, honestly. There's over 11,000 materials in the Moldflow database. Not all of them are fully characterized. Moldflow, with every release of the software and even intermediate releases, tries to do what they can to clean up the database, meaning getting rid of old materials, getting rid of materials that are just poorly characterized in general. But there are quite a few materials that aren't fully characterized. They may not have CRIMS shrinkage data, for example, for your midplane and dual domain models. They may not have the juncture loss data. So they will keep materials in there that will give you enough data to actually be able to run analysis, but it may not be fully characterized. So that's where the analyst expertise comes into play. You really have to make sure that you have really good data, especially with windage. Okay, I think with that, we will close it out. We do have all the questions that were submitted, and we'll try to get back to you on those when we can. I want to thank everybody for taking the time out of your day to do this. Again, we'll have another one in a couple of months in May. Check us out online to get registered, and I'm sure you'll see an email or two to get you signed up for that as well. You can always contact me through email or by phone if you have any questions. So thanks again. I appreciate your attendance and have a great day.